Welcome to the Maintenance and Reliability Professional Review course. Today's lesson, Lesson 4, will cover Equipment and Reliability 1. This slide shows how to contact me, Dave Krings, your instructor for the Maintenance and Reliability Professional Review course. As always, the best way to contact me is through my email address at dkrings@masteringmaintenance.com. Today's objective is defined by the Pillar 3 explanation from the Society for Maintenance and Reliability Professionals Certifying Organization. It's actually a twofold objective. First, we're going to assess the current capabilities of the equipment and processes in terms of their reliability, availability, maintainability, and criticality. Second, we're going to select and apply the most appropriate maintenance practices for the equipment to deliver their intended capabilities in the safest, most cost-effective manner. Let's take a look at the agenda for Lesson 4, Equipment and Reliability 1. First, we're going to establish equipment and process performance expectations. We talked about this a bit in Lesson 3, and we'll continue to expand upon it in Lesson 4. Second, we're going to measure the current performance of the process and identify the gaps. Third, we're going to design a maintenance strategy to assure performance, and this will continue on through Lesson 5. Lessons 4 and Lesson 5 will cover the entire pillar number 3 of equipment reliability. This slide, which should be very familiar to you by now, as it's in all of the lessons, shows the 5-pillar arrangement and the fact that we're moving into the third pillar of the 5, equipment reliability, as shown in pale green on the left-hand diagram and pale green on the right as well in the pyramid. As you can see, we're building upon the program. We've got business and management covered, we've completed manufacturing process reliability, and now we're going to spend 2 fairly complicated and long lessons, Lessons 4 and 5, on equipment reliability. There's a lot of meat in these 2 lessons. It's very important that you understand and can apply these topics as you move along. So let's begin. The first objective for today would be to determine equipment and process performance expectations. And to kick that off, we need to identify business goals that must be supported by maintenance and reliability strategies. This should sound familiar because it's the same thing we talked about in Lessons 1 and 2 of business and management, except now we're talking about specifics. We're going to take a look at changes in sales goals. If the organization is looking at changing the way they market and sell their products, we need to know about that and we need to react to it in a proactive manner. The maintenance and reliability strategies should support the plans of the marketing and sales group. So if there are going to be changes in production goals, for instance an increase in sales based on marketing expectations, or a change in the product mix, we need to know about that. In general, if you're making less products and a simpler product mix, you can generally make higher productivity in an operation because of less changeovers. So we want to know about that, and also we want to know if more products are going to be coming through the production line because it will affect how reliability deals with that. Continuing along in the same topic, identifying business goals that need to be supported by the maintenance and reliability strategies, another aspect is changes to the production processes. If we know that new equipment is going to be installed in the plant or on a process, we should be taking that into account as we build the maintenance and reliability strategies for the affected area. We also need to know if there are going to be new uses for the existing equipment. It's not uncommon in a lot of industries to move equipment around and change its purpose. Sometimes, depending on the application, equipment will behave quite differently in 2 different applications. So we need to know about that and take it into account if we need to correct the way preventive maintenance routines are set up for the equipment, record keeping, spare parts inventory, etc. Continuing on with identification of the business goals, we have to talk about changes to staffing levels. Many companies are under a lot of pressure to reduce staffing, and the plan for these reductions needs to be taken into account. Maintenance and reliability requires qualified, skilled individuals to do the work. And a proactive maintenance initiative is going to make it that much easier for you to handle reduction. It isn't necessarily true that improving the proactivity of your maintenance program will allow you to reduce staff, but it'll definitely make it easier for you to keep up as the breakdowns disappear. Second, consider how reliability must adapt. It may change the way roles and responsibilities are divided based on the staffing reductions. Next, where necessary, justify positions to support reliability. If there is a reduction plan and some of those reductions are targeted at the maintenance department, you may want to take a second look at how these reductions are going to affect you, because the roles and responsibilities of many people in your organization will be affected as you change to a more proactive operation. It may be possible to justify retaining some staff that were scheduled for reduction just to support the reliability program. There could be enough cash savings to justify it and make it very easy for you to keep your staff. Another issue to keep in mind while identifying business goals that must be supported by your strategies are changes in budgets and capital spending. Depending on economic conditions, companies change their budgets and they change their plans for capital spending to coincide with the economic conditions. So if things are really booming and your company decides to add some more process capacity, your maintenance and reliability strategies should be flexible enough to adjust. One calculation that's very helpful in determining equipment and process performance expectations is availability. We touched on availability a little bit under operating equipment effectiveness in the calculation from Lesson 3. But let's take a look at availability once more, because it has a couple of different definitions and I want you to understand their application. Availability, as we talked about before, is defined by a formula: available hours divided by total hours times 100%. Available hours is equal to the total hours minus the downtime hours. This is a really simplified view of it, and there are some different caveats to this depending on how you calculate your downtime hours. But there are two basic schools of thought. Number one, that the total hours in the denominator includes only hours of planned production. In other words, if your operation only runs 8 hours a day, the total hours available is 8, not 24. The other school of thought, number two, is that total hours is a 24-hour, 7-day-a-week figure. Well, let's take a look at this. Why would they be useful, and why would you want to have two different definitions for the same calculation? Well, there's a good reason, and let's look at this example to see. Let's calculate the required process availability in an example. As I told you before, the definition of availability is shown at the top of the slide. And here's a little short word problem. If a plant plans to run 8 hours per day, 5 days per week, and its main process line operates for 37.2 hours during that time, what is the process availability? Under Method 1, availability would be equal to 40 hours minus 2.8 hours, which is the 2.8 hours the machine or process line didn't operate, divided by 40 hours, which is the total available hours based on the production schedule, times 100%. Gives us an answer of 93% availability. This number tells us how effectively we're using the planned uptime on the machine. Not too bad. Now let's take a look at Method 2, which counts hours around the clock. This shows that the availability would have been 168 hours if you were running 24/7 during the whole week. And the 130.8 hours that we were not operating is basically the off-shift hours plus the downtime hours during production, divided by 168 hours, which is the number of hours in a week, times 100%, which gives us 22%. Quite a disparity from the 93% in Method 1. Well, why would we use these two numbers? The first one is really useful for measuring the availability inside of the framework of what your production intentions are. So it tells you how well you're using the time you plan to use. The second availability figure is useful in telling you what the maximum output of your operation should be. In other words, in this example, this same plant if its rated capacity will allow it, could generate almost 5 times as much productivity as it does under the current circumstances. Well, this is useful for planners to decide if we should add another shift or possibly 2 shifts depending on demand for the product. You certainly wouldn't need to buy new equipment if the equipment's designed to run for more than 8 hours per day. This is an interesting example, I think. Another thing we need to do is establish a maintenance plan resources budget. 1. For labor costs. We need to continue routine tasks that will continue. What would those things be? Planned work, preventive maintenance, predictive maintenance, some breakdown work, training, many different things of that nature. We need to consider the impact of new added tasks. Well, there probably will be an increased load on training as you become more proactive, because proactive operations require lots of training to keep their skills up and to plan for the future. We need to consider the learning curve. As we change the way people do things and we modify the process to make it more efficient, at first it's going to take more labor because people are learning, and when they're learning, they're slow, and it takes time for them to become comfortable and adept at doing things a new way. After a period of time, when the learning curve goes away, things will be more efficient than they are in the current situation, and you'll have to take account for it in the other direction. Last, consider the elimination of wasted time. Believe me, in a reactive maintenance operation, there is a huge amount of wasted time at all levels. This wasted time will rapidly disappear as your new process takes hold. As we continue to establish the plan resources budget, we also need to consider the costs of spare parts and replacement parts. We need to start with a baseline of our storeroom and replacement part inventory plus inflation, for example a 2 or 3% increase per year. And then we need to consider the changes that are going to occur. First off, there probably will be some plans to attack problem equipment that is chronically failing or chronically consuming man-hours. So you'll want to take that into account if it's needed to add more spare parts into the inventory while you attack the problem, and then to account for those parts going away as the problems are resolved. Second, you might want to take a look at the impact of criticality calculation. In fact, I know you will, because when we do a criticality calculation, and we'll look at that in just a little bit, it's going to give you a much clearer picture of what equipment in your process is really critical and what equipment is not. It doesn't make a lot of sense to store storeroom inventory on site for parts and for equipment that is non-critical. The definition for critical is a fairly concrete one. It's easily calculated. I think you'll really like the technology that we use for that, and just bear with us. In a few minutes we'll look at it. Third, the impact of bills of materials. If you don't already have your entire storeroom inventory tied to the equipment with a bill of materials, then you really don't know what parts are for what equipment and why you even have them. In many cases, particularly in older operations where computer technology didn't exist when the storeroom was begun, spare parts inventory could have gotten quite out of control because things are normally stocked when they're needed and documented poorly and then utilized throughout the plant, even on equipment that they weren't intended for in the first place. You need to get this resolved because it's really the key for how you can reduce storeroom inventory in the future. A bill of materials ties each part to the equipment it's used on and tells you what it's for. After you have that, you can do a very nice report in most CMMS software, and actually most ERP software as well, to figure out where the parts are needed and where they're not. Let me give you an example. If you have done the criticality calculation on all of your equipment and you have a list of what's high criticality, what's medium criticality, and what's low criticality, and you have bills of materials for all of your spare parts, then you can run a list of spare parts that are stocked for low criticality equipment. This is a great place to start in reducing your storeroom inventory because these parts are probably not necessary if the criticality calculations are accurate. It's a really great place to start, and it's a fairly low risk situation to get rid of those parts. Fourth, the impact of planning and scheduling work. Planned and scheduled work does not consume parts from storeroom inventory if it's done correctly. Planning allows you to order parts from vendors and outside sources, You shouldn't really be drawing down your storeroom inventory when you're planning. That's why you plan in the first place. So, the impact of planned and scheduled work should be to reduce storeroom inventory. The impact of precision maintenance, preventive maintenance, and predictive maintenance. Preventive maintenance and predictive maintenance don't generally use a lot of parts, but if they do, they're usually low-cost, replaceable parts such as filters. Precision maintenance generally allows machines to run longer than they did in the past, and generally speaking, in conjunction with predictive maintenance, precision maintenance will create smaller failures that are easier to correct. For example, you may not need as many bearings and seals and gears and metal mechanical parts as you had in the past because the failures are going to be more subtle. Anyhow, expect that there will be some changes as you become more precise in your maintenance. Another aspect of measuring and determining the equipment and process expectations and establishing the maintenance plan resources budget is the cost of external contractors and services. This can be a significant portion of the maintenance budget at a site. Some sites may increase the use of contractors under a proactive maintenance arrangement. It is one of the things that some sites feel reduces their costs because contractors can come and go. They don't need to come to work every day, only when the work is there for them to do. And it also reduces the cost of benefits at times. However, the hourly cost for contractors is generally quite high compared to full-time employees within a facility, so it needs to be looked at from a cost standpoint. Some sites will reduce or eliminate contractors over time, and this is actually a best practice in a lot of systems that have taken a look at it in depth. But they've reduced the amount of contractors down to the point where almost all work is done internally. It just depends on your operation. It sometimes makes sense and it sometimes doesn't. Third, plan to use contractors during the early phases to bolster abilities during the learning curve. State this clearly when you start. What I'm trying to tell you here is as you're going through the learning curve, some things that your maintenance and reliability staff have handled in the past is going to be very difficult to complete because they're going to be so busy doing training, building the process, measuring, doing analysis to figure out action items and making changes, as well as adopting new activities that they never did before. So it's going to be unrealistic to expect that maintenance staff is going to be able to do project work, discretionary projects that you normally would have done with them in the past, and some routine training may have to be rescheduled as well to make it work. So I'm just cautioning you in the first place that you may need to use contractors to do work temporarily, and it could be a particularly tough issue, especially in a union environment, so you might want to talk about it early and make a plan for how you're going to deal with it appropriately. Let's discuss the cost of interruptions due to maintenance or failures. As you're building your maintenance resource budget, you're going to need to take into account that there's going to be some production interruption due to maintenance or failures. This already happens, it's not a new thing. So you can establish a baseline fairly easily based on the past. Then, as you start adopting your maintenance initiative, you're going to have to add in some extra time for mistakes and errors during the transition. Almost every site, when they start adopting proactive maintenance, will see somewhat of a rise in interruptions and waste during the transition, and it's generally not a very long period of time, but it's something to be expected and communicated to the leadership so that they don't make the mistake of giving up just because there was a slight rise in interruption. Third, you're going to start seeing some effects that are going to be a positive thing for you. Reliability improvement is going to cut down the amount of interruptions to your production process. I would expect this to start happening between 1 to 2 years after you start the process. It might happen sooner, but generally speaking, it doesn't really take effect until about 12 months after you start. And if things are really difficult during the transition, it could be longer. Fourth, remember that you're going to have improved response time as you get rid of breakdowns. Because there's going to be more planning and scheduling, and work is going to be more structured, there should be less interruptions, the work should get done much faster. As I mentioned before, it's 4 to 9 times cheaper to do planned work. Well, along with that is an increase in speed. One thing that I've seen happen over a period of time, when we've gone from reactive to proactive maintenance in an operation, is the amount of time it takes to execute a job drops by about 75%. I've measured this both in mechanical and electrical and instrumentation type work, and it seems to hold fairly close. If it was an 8-hour job in reactive mode, it'll run about 2 to 2.5 hours of actual wrench time work after you become proactive. It just works out that way for some reason. The other thing is you need to take credit for some improved early detection. As you become more adept at doing good preventive maintenance and your predictive maintenance program comes into its own, it's going to start collecting enough information to avoid failures and predict them much earlier. So what will that do? Well, for one, you're going to be fixing less breakdowns, and you're going to be doing more minor repairs before the actual failure occurs. So when you have this early detection, it gives you time to plan, and when you do finally do the work, it's much simpler and easier work to do than you would have had if you ran to failure. Moving into another objective in Lesson 4, establishing current performance levels and gaps. As we've talked about in the past in Lessons 1 through 3, quite a few times we need to measure current performance levels and gaps in various parts of this initiative. We're coming back to this full circle again, looking at ways that we can close the gaps between reactive and proactive methods. In the beginning of this, we need to prioritize to assure that resources are appropriately allocated. Do we have things being done in the right places at the right time by the right people? So let's talk about a concept. We talked about this briefly a few slides back. Criticality. Criticality is a structured calculation to determine the relative importance of each piece of equipment or process based on a number of things, including safety, its environmental impact, the quality effect on your product, the production volume, and other special causes. There are a number of different ways to calculate criticality, all fairly close to the same basic idea, and we're going to take a look at an example. This is a simple criticality example just to illustrate how it basically works. When you need to calculate criticality, you need to make a spreadsheet or some kind of a chart that shows all of the major equipment in your facility. In fact, I would recommend all of the equipment that you ever do repairs on be included in this criticality calculation. And one thing that you can do to make the work a little bit simpler is to group the equipment by process. Because, for instance, if a process itself is critical to the operation, then all of the equipment in it that drives it would also be of the same criticality, or greater. So let's take a look at this example. It only has 6 pieces of equipment in it, and we didn't even use equipment numbers just for clarity. But let's look. On the far left of the table, we show the equipment that we're going to discuss. A nuclear reactor, a waste treatment plant, a turbine generator, a safety shower, a spare supply pump, and a coffee maker. Some of these things are actually processes themselves, but let's just talk about this in general terms. As we mentioned on the slide before, we consider things like safety, the environment, quality, production, and special causes. We've left off special causes on this chart for clarity. Really what we're talking about there is if you have a piece of equipment that has a special reason to be considered high criticality, then you should give it some weight. For instance, I'll give you an example. Many facilities, because of their size, have electric golf cart type equipment for moving personnel around the facility, and generally those are considered a convenience item. But if you have a person on your staff who has a disability and isn't able to walk or move around in an efficient manner, then you need to give them access to a cart like that, and normally an electric golf cart would be a low criticality piece of equipment. In this situation, however, it's vital to that person's success, and it would be considered high criticality. I'm sure you can think of other examples similar to that. So let's take a look at this. Really, on this spreadsheet, we have safety, the environment, quality, and production shown on here in each table. And also, next to those basic headings, which you can see in color there, is a small field for showing the weight as far as criticality is concerned. And all that's for is to give each of those aspects a generalized weight compared to the others. In most facilities, safety is the #1 priority above all else. So you don't want people taking shortcuts with safety to increase production, for example. So normally the weight on the safety calculation is scored the highest. You may choose not to do that. Some sites choose to have the same weight across the board. It really doesn't matter. It's just a tool for giving more weight to one particular aspect than another if it makes sense. Environmental concerns are generally weighted fairly heavily. In this case, I placed it at a 70, for example. Quality and production are also important, but I weighted them slightly less at 50 and 30 just to differentiate them from safety and environmental issues. Okay, so now when we go down into the spreadsheet, you'll see that underneath the score column, I've scored each of these pieces of equipment under each relative category, for instance, safety, the environment, quality, or production, on a scale of 1 to 10. You can do this a different way if you'd like, but 1 to 10 seems to work very well, with 1 being no effect, and number 10 being maximum effect underneath that category. So let's take a look at those yellow fields. A nuclear reactor, if it were to fail, could have a very major impact on safety, so I scored that a 10. I did the same thing under the environment, because if the nuclear reactor was to melt down, we would have an environmental catastrophe. Normally, a nuclear reactor would be producing electrical energy, ultimately, so quality and production would also be affected if it were to fail. So I scored it 10 across the board. Now here's where the weights come into play. The weight is calculated against the score that we just gave it in the safety score column, for instance, the environmental score, quality and production scores. So let's take a look at safety. The nuclear reactor was scored at a 10, multiplied times the weight gives you a raw score for criticality of 1,000. That same kind of math goes across the spreadsheet in each category. So you'll see that under environment it scored a 700, a 500 under quality, and a 300 under production. The sum of those four scores is shown on the far right under results total, and the score for the nuclear reactor under raw criticality total is 2,500. Same logic holds true for all of the calculations all the way down to the coffee maker, which has a low criticality across the board if it were to fail. Now you might argue that if you're a production person working 12-hour shifts at night that your coffee maker is a high criticality piece of equipment, but in reality, when calculated based on the facts, it's just not the case. You'll have to get your coffee somewhere else if it breaks in the middle of the night. So anyway, taking a look at these different examples, and in your case you might have different beliefs about the scoring. The big thing is that at your site these scores need to be reached through consensus between maintenance and operations. Anyhow, you can see that the nuclear reactor scored a 2,500 and the coffee maker scored a 250. So it's very easy to see what's a high criticality and what's a low. And I would say that this would be fairly typical of the range between the highest and lowest pieces of equipment in a plant. Later on in, I believe, Lesson 9, we'll be taking a look at how this criticality distribution looks if you put it into a chart, and how you can decide where to draw the line between high, medium, and low criticality. Continuing on with prioritization to assure that resources are appropriately allocated, the next topic would be capacity. There's only so much work that can be done in a given day by the resources that you have. So you need to load level those resources and make sure that you're not overloading any one in particular or any process in particular. There's something to keep in mind, that if you don't have the capacity somewhere where you really need it, it needs to be addressed, and that might be included in your gap analysis. The next aspect would be cost. We need to be prepared to justify all decisions based on cost. So if you're recommending that the maintenance and reliability initiative include something, you need to be able to talk about it in dollars. No other terms are going to make sense to your leaders, and they're not going to be compelling. Some decisions are very clear and others are not. As I mentioned before, it's going to be difficult to measure some of these things, but you're going to have to take the time to do your homework and get the facts. We also need to apply metrics to assess current conditions and capabilities. You want to do a really good job of assessing where you are so that you can measure where you want to go. Some of the measures that are very popular in maintenance and reliability would be mean time between failures, or MTBF, the failure rate, the mean time to repair, which is also looked at as MTTR, it's also called maintainability, incidentally, and repair rate. If you cannot yet measure these, you should start now. Take a look into it, do some research, and choose measures that are useful to you that other people are going to be able to understand. Acquire the data tools that you need to get these numbers, and really at the root of that is a good quality computerized maintenance management system. Here's another important measure: maintenance cost per unit of production. Be careful here, because people are going to throw this number around and they're going to tell you that they have X cost per ton, and you're going to be trying to match up to that because you're in the same industry. Very tough. It's a dicey situation because many places measure their maintenance costs differently than others. You need to make sure that you take the time to be careful and define what maintenance means at your facility. We're going to talk about this in a couple slides here as we move along. But the maintenance cost per unit of production is only relevant inside your facility unless for some lucky reason you're in an industry where this is a standardized calculation. If it is, well, then you got a little bit of an advantage over the rest of us. But maintenance is often tangled up in non-maintenance activities, and we'll see that in just a minute. Let's take a look at what the definition of maintenance is. This is a definition that I've seen used, and I happen to agree with it. It's the upkeep of existing assets at their full rated capacity in their current configuration and application. Well, this little statement says a lot, and it also kicks out a lot of things that you know your maintenance people do on a day-to-day basis. Let's take a look at that. What is not maintenance? Well, the installation of new equipment is necessarily not part of maintenance. If maintenance only includes the upkeep of existing equipment, you're not maintaining anything when you install new equipment, so it's not really maintenance. So the cost of putting in a new piece of equipment, even if you're using maintenance personnel, should not be included in a maintenance cost per unit of production calculation. Next, major modifications to existing equipment. That's not maintenance. Maintenance is the upkeep of existing assets in their current application and condition. Well, major modifications doesn't fit in there. Capacity increases. Breaks the rule. Under the maintenance definition, it's at their current capacity, not a capacity increase. Fourth, building shelves, building small shacks, building picnic tables, wood stoves, hot rod parts, etc. is not maintenance. Now, none of this happens at any facility I've ever been to, and I don't know if it happens at your site, but building things and doing government work projects of this type is not part of maintenance. It's just something that people tend to want to do. If you want to take it just a little further, I'd like to point out that there's one other thing I don't show on this slide that is also not technically maintenance, and that's repair. Repair is really fixing things that failed. Now take a look at that definition back one slide and realize that it says it is the upkeep of existing assets at their full rated capacity. A breakdown really doesn't fit into the maintenance definition either. Breakdowns are failures. That's not maintenance. You're not maintaining anything when you're having breakdowns. So I would really encourage you to try to get away from breakdowns and eliminate them. So we're going to apply these metrics and take a look at some more of them. Equipment availability. We've done two examples already that utilized availability, and you should continue to use availability as a kind of a barometer for how well your equipment is operating and how well your reliability program supports it. First off, you need to ask yourself the question, are you satisfied with the current availability of your processes and equipment? If the answer is yes, then you're a little bit ahead in the game. If it's no, now you've got some ideas about how you can attack it. Number two, are you utilizing all of your equipment wisely? I've been in facilities before where they had twice as much equipment as they really needed to accomplish their tasks, and of course they had to maintain all that equipment. Was this wise? I think after taking a look at maintenance and reliability techniques, the company itself decided that it really wasn't necessary to have that much excess capacity, and the elimination of unnecessary equipment is the best maintenance you can do, because you don't have to fix things that are gone. Do you maintain more equipment than needed? Well, I think the example I gave you pretty much shows that it does happen. If you have equipment that you can eliminate, or equipment that you can simplify, this is great. Now here's another point that we talked about already: process availability or system availability. You can calculate availability across a whole process rather than just one piece of equipment. And this is not that complicated. It's just basically the compounding of the same calculation across multiple pieces of equipment, and it's easily measured. Typically, you can get this information from your distributed control system or from your CMMS. But if you don't have those tools, it's time to start thinking about an upgrade. Scrap rate is another thing that you can take a look at. If you're making a lot of scrap in your production process, wow, that's a place to eliminate waste, and it's free profits if you can get rid of it. I know some of this is inevitable, especially in industries where you do a lot of trimming on the edges of your product, such as the pulp and paper industry, the steel making industry, the lumber industry, for example. But if you can find ways to reduce scrap or find ways to utilize it in the process, you're money ahead. When looking at the current conditions, production delays is another thing that really can have a big payoff. So I would suggest that you utilize lean manufacturing techniques and lean maintenance techniques to increase the speed of your process and reduce waste. Lean manufacturing says that if you've got a lot of work in process, or WIP as they call it, in between different steps in your process, you've built in delays that are costing you money. And when you utilize lean manufacturing techniques, you can squeeze those bottlenecks out of your process, improve the process speed, and reduce waste. Another handy useful measure is total maintenance cost as a percent of the assets. This is kind of a 30,000-foot view showing the relative efficiency of maintenance and the relative process reliability. As your asset value goes up and your maintenance costs go down, you should see this ratio dropping, of course, and it tells you that your maintenance dollars are carrying you further. Forces operation also to balance their costs and avoid over-maintaining to get maximum reliability. In other words, this number won't let you hide by doing 1,000,000 PMs on your equipment so that it never fails. The cost of all the maintenance that's done will be taken into account. Another handy figure is replacement value. The replacement value of the entire process can be calculated, much as an insurance company would do to make a policy for the company to protect it in case of a hazard, for instance fire or flood. Next, replacement value can be used to help in planning and justifying maintenance efforts. If you have a high value piece of equipment or a high value process, spending some money to maintain it will be easy to justify. Replacement value also gives you a nice window into the repair or replace portion of your decision making. If you have a piece of equipment that has absolutely no replacement value and it's fairly easy to maintain and it produces well, it might make sense not to replace it if it's doing the job. Here are some of my favorite measures: percent planned or unplanned maintenance. It's a good goal to shoot for 80% plus planned maintenance, calculated in hours, not the number of jobs. If you're not doing at least 80% planned maintenance, you're not even in the game as far as reliability is concerned. And most places are doing less than 10% planned maintenance if they're in reactive mode. They might think they're doing better than that, but they don't have a good definition of what planned work really is. I've seen facilities say that they're doing 100% planned work just because they took the work orders and printed them out on a list. This is not planning. We're going to talk about this in a lot of detail up ahead here a little bit in the lessons. But rest assured, planning's not a make-work job. This is a hard thing to do, and it takes some time and dedication. Let's talk a little bit about maintainability. As I mentioned a few slides back, maintainability is the same measure as mean time to repair. It's just a measure, a relative measure of the ease of maintaining a piece of equipment. If the mean time to repair a certain type of pump in your facility is 2 hours, and another pump that does the same kind of work can be repaired in a meantime with a maintainability of 1 hour, you have a definite advantage to use that second pump. That second style of pump is cutting half of the maintenance time off. Now, here's something to keep in mind. If that pump fails 5 times as much as the one that takes longer to repair, you don't really have a good deal. You need to look at a lot of different factors to decide which piece of equipment is the best. Third, maintainability can be changed. The figure itself can be changed by modifying the equipment itself to make it more reliable or easy to repair. You can do it with better tools, and you can also improve the skills of your craftspeople, which makes them work faster too, which allows them to maintain the machine quicker. So maintainability is a relative measure, and you really don't know why the number would change unless you're paying attention and applying these techniques one at a time so you can get a measurement. The delay rate. I don't have a whole lot to say about this one, but really what we're talking about here is how much time is there involved in delays before the repairs can be executed. Generally speaking, this is kind of the same thing as measuring the response time for the maintenance crews, and it really isn't that much of an issue once you get to be a proactive maintenance operation, because there won't be any delays. Everything will be planned and scheduled, and people will be on site ready to work on time. As we continue to establish current performance levels and gaps, we need to identify current opportunities for improvement and potential performance shortfalls. Changes in operations affect maintenance. Let's take a look at that. First, the maintenance department needs to know the process so they can understand what's going on. As changes in the process occur, the maintenance department should care about it just as much as the production staff. Know what the production changes are and what they're planned to do. Stay involved and stay current. This information is useful to you for building a better reliability process. And fourth, help the production departments avoid mistakes. The production departments don't generally know the technical details of how a maintenance and reliability organization will react to different changes to their process. It's very important that you get a chance to give input when it's early enough to make changes if it's necessary. As we continue to identify current opportunities for improvement, we need to talk about changes in performance expectations. As we convert from a reactive to a highly proactive maintenance program and work on this initiative, the performance expectations for the maintenance department should be rising rapidly. There should be a clear understanding that the maintenance and reliability of the production department really relies on the maintenance team doing a good job and being responsible for its own performance. If in the past it seemed like the production departments were driving what maintenance would do on a given day, this should be changing. The maintenance department needs to take ownership, and it should be responsible for everything it does every day. Inadequacies in the maintenance practices are going to become rapidly evident as you become more proactive. You need to identify them, and they may be of different types. For instance, your training may be inadequate. You need to revamp it or modernize it. Your work order management system is probably suffering somewhat, especially if you don't have a computerized maintenance management system. Your planning and scheduling operation may not even exist, as it doesn't in a lot of reactive maintenance operations. If it does, and you're partially proactive, you may still need to make some adjustments. Work prioritization is a common place where some inadequacies exist. Generally speaking, communication is always a challenge at most facilities, and there's always room for some improvement. In particular, follow-up, root cause determination, history records, and documentation can sometimes fall on the back burner as breakdowns control everything in a reactive maintenance operation. If you don't have people that are dedicated to doing good follow-up and analysis and root cause failure determination, and someone who's documenting their work, and actually all the maintenance people should be experts at doing documentation, then your history records are going to suffer, and you're not really going to be able to eliminate failures permanently. As you build your new proactive maintenance organization, you're going to identify some new maintenance requirements. First off, your predictive maintenance tools are going to probably advance. You're not going to be doing just some vibration analysis any longer. You're going to be looking at some other highly advanced technology. We'll talk about that a little bit later. Next, there's always a kind of a trend for legally required tasks to increase as the government becomes more and more involved in things to protect the environment, protect the safety of workers, and also just to regulate things because that's just what they do. Third, new equipment needs. As technology advances and new things become developed, new equipment comes into play, and that requires new technology to keep it operating at its best. Improved documentation. Improved documentation is going to drive a great deal of your process. As you build that documentation, there are going to be requirements for maintenance to collect more information and keep it in a place where it's much easier to access. In other words, keeping things in a file cabinet in an office is no longer adequate. There needs to be an electronic system to share documentation, to make sure that everyone can see it, and to make sure that everyone has access to the latest and greatest copy. And last, do you think you need a new computerized maintenance management system or ERP system? Most facilities have some type of software that they're using to track their maintenance work, but I tell you, in the last few years there have been some huge advances in the way maintenance is managed. If your tools are more than 5 years old, they're probably completely obsolete. There are some really great new tools out there, and you should be keeping up to date on these because, yes, it's a great tool and it can be very expensive to replace, but there are some things that are out there that have come on board in the last few years that really make it worth your time to do it. And in particular, one of the things that's really changed is the new systems are easier to use, easier to understand, and they look a lot more like the other things that you do on your computer. They're Windows based, they can be web based, and they're much easier for people. There will be some opportunities to apply new technology as well. This is a wide open area with lots of opportunity. Now, I would caution you to use the applications and the new technologies where they make sense, but be careful not to fall for the shiny toys. Most operations that are looking for an improvement in performance tend to drift toward using technology or looking at doing things that are on the high end of our pyramid for the 5 pillars. In other words, they want to do it by using preventive, predictive maintenance, condition-based monitoring, and fancy doodads that go along with that. If you don't have a good process built at the foundation so that your equipment is maintained to be reliable and your process is designed to support that equipment, no matter how much technology you pour on top of it, you're never going to get there. Remember that the process is based on fundamentals. If you don't have the fundamentals, there's nothing that will save you, no matter how much money you spend. Technology will not fix a broken process. Let's look at identification of this opportunity for improvement. Chronic problem equipment. Every facility has some equipment that keeps eating their lunch. You have equipment that has more failures than any other. And you can walk through the department and talk to maintenance people and they can readily tell you what that equipment is because they spend a lot of time buddied up to it. I would recommend the use of top 10 lists, and we're going to look at that in more detail in a couple slides. The other thing is, you can run reports if you have a good CMMS package. They'll tell you what the chronic equipment is even if your people don't want to tell you or don't have a good idea. You can look at equipment history and see where the time and money is being spent and so forth. But people really do know what equipment is a problem, so just ask them. So here's the PDM top 10 list. PDM meaning predictive maintenance top 10 list. Really, you can use these top 10 lists to your advantage at all times, and we're going to talk about that in a couple of different veins of thought shortly. But let's just look at some top 10s. The first one being the top 10 causes of lost production. You could focus on those, and you could really make some big gains by just fixing a few things instead of thousands in your facility. Look at the top 10 most costly machines to maintain. Look at the top 10 consumers of maintenance time and the top 10 causes of product defects. If you took these 4 top 10 lists and destroyed them, I can tell you that your facility would be a changed place. If you focus on the top 2 in each of these categories, you could reap huge rewards. As we'll take a look in a few minutes underneath the Pareto chart discussion, 80% of your failures are caused by 20% of your equipment. And that holds true in a lot of cases. It just seems to be a rule that most things adhere to. Let's take a look at root cause failure analysis, or RCFA, as a method for identifying current opportunities for improvement. Root cause failure analysis is just a structured method to determine the root cause of chronic failures using a logic tree. The first thing at the top of the tree that we would put down on a piece of paper is the failure event itself. Then we would go down one level in the tree and list all of the possible failure modes. In the next level, we could hypothesize how these failure modes are occurring and verify that those hypotheses are all valid. Below that, we have three types of roots that we can look at to verify what is causing the actual failure. We have physical roots, physical information that we can look at that could be the cause and verify that those are all valid. We have human roots. Human error is the cause of many different failures and can contribute to failures that are a compound of two. But at the very base of the root cause failure analysis logic tree are what we call latent roots. And if we can list those latent roots, which are the things that are the true root cause of the failure, and verify that they are all valid, we then have a complete picture of the piece of equipment and its failure and the possible causes. As we go through this analysis and take a look and eliminate each of the possible causes based on the facts, we will eventually determine the root cause of the failure and be able to take action that really does have an effect for the long term. I encourage you to spend some time looking into some of these concepts as we go through the lessons, because necessarily in lessons 1 through 9 we're only going to spend a few hours together talking about many different concepts, and if you see things that you don't know a lot about and I don't cover in enough detail for you to feel comfortable, take some time and do a little research, because we could literally turn this into a college degree and spend 4 years together working on lessons, and root cause failure analysis is a big field. So make sure that this is just an introduction and you can take the time to go into it as deep as you'd like. I mentioned a few slides back that we would take a look at Pareto analysis, and we'll do that on the next slide because I have some graphics to show you. Let's take a look at the Pareto principle, or the 80-20 rule as it's sometimes called. This calculation was put together by Wilfredo Pareto, an Italian statistician, and he found that in a lot of cases processes react in the same exact way, and how we can apply it to the maintenance process is quite clear. Let's take a look at some examples of how the 80-20 rule applies to equipment and failures. Under Pareto's principle, 80% of all failures are occurring on 20% of the equipment in a given process. And it's really surprising how well things hold to pretty much this same ratio at all times, 4-to-1. Next, another one that would hold true. 80% of the spare parts needed in the storeroom are contained in 20% of the total storeroom inventory. No matter how small you cut the storeroom inventory down, you'll find that this 80-20 rule still holds true. It's very strange, but it's true. So this rule applies to most process variables in maintenance and reliability, as well as other fields. So I would encourage you to focus on the 20%, because you can work on a smaller group of equipment, a smaller piece of a process, and get great results for a lot less money. Now let me give you an example here. Let's say that in your facility you have 10,000 pieces of equipment, and you're just setting out on your maintenance and reliability project and you want to make a big bang for the buck. Well, 10,000 pieces of equipment is a lot of equipment, and it's really tough to focus in on which ones you should work on first to improve reliability, right? Well, not necessarily so. If you have information in your CMMS about where you've been spending your time, or you can put in the CMMS and start collecting it now, very quickly you can figure out where you're spending your time and your money. So if you take the 10,000 pieces of equipment and you sort it from most expensive to least expensive and take a cut off the top, take the top 20%, and now you're down to a 2,000 piece of equipment list. Well, that's still a big number. 2,000 pieces of equipment is a lot of equipment. So let's cut it one more time. Take 20% of the 2,000, and now you're down to 400 pieces of equipment. Well, 400 pieces is a little bit more manageable, but still a little bit thick. So let's cut it to 20% of 400. Now you're down to 80 pieces of equipment. 80, you can fit that on one piece of paper. So take those 80 pieces of equipment and rank them from highest to lowest and start working on making those 80 pieces of equipment as reliable as possible. They're the big 80 hitters in your group. They're the 80 most expensive pieces of equipment in your facility. Now do the math. We just cut that list 3 times, from 10,000 down to 80 pieces of equipment. Now if you take that and compound it and calculate the fact that you're getting 80% of the value out of each of those steps, we're reducing our impact on the process every time we take some equipment out, but not that badly. After 3 cuts, we're down to a 1-page list of equipment. If you make those 80 pieces of equipment reliable and eliminate their chronic failures, you will cut your maintenance work by 51%. 51% of the equipment failures in your facility will be gone. Do the math. It's surprising, isn't it? Here's another thing to identify for opportunities for improvement: a bottleneck analysis. Every process has bottlenecks, places that hold up the process from going any faster. You should identify those bottlenecks in the process. And the funny thing about it is, once you eliminate one, you create another. That's always the case. But you're trying to streamline your process, and you push these bottlenecks around all the time. Look for places where work in progress, or WIP, is sitting idle. Those are places where waste is occurring. You don't want a lot of junk sitting around in between on processes. If you have inventory that's half processed sitting all over the floor in your production system, then you need to do something about it. It's really not a maintenance issue, but it definitely affects reliability. Now, removing these idle points, which applies to production and maintenance, work orders and everything, is something that everyone should be focused on. So the maintenance process is no different than a production process. Look for the bottlenecks. If you have a monster pile of work orders sitting in front of your planning organization and they're unplanned, something's wrong. You're either not staffed up properly for planning, or you're letting way too much work go through your process, or there's something wrong with your reliability, or something else that's causing that bottleneck. You shouldn't leave it that way. It should be dealt with. Okay, now we're going to get into something a little deeper. This is called Weibull analysis. Weibull analysis is a tool that you can use to look for opportunities for improvement. It's an analytical method to calculate the life of equipment based on past performance. It's useful in choosing new equipment, predicting repair events, planning overhauls, etc. This is pretty deep. There's a lot of calculation involved in it, and I've got a formula shown on the screen here that kind of shows the basic formula that controls the Weibull analysis calculation. It doesn't look like something that you would use every day. But I will tell you that Weibull analysis can be used and properly applied by someone who uses it in reliability to calculate which piece of equipment is the right one to buy or the right one to use in a certain application. Now, with the use of computers, some of these Weibull analysis uses are becoming much more easy to use for the average person out in the field, and some CMMS software uses it transparently so you don't even see these formulas, and it can be used to make decisions every day. I encourage you to take a look into Weibull analysis. It might be something that you can use to improve the reliability at your plant. Let's take a look at identifying maintenance required for new equipment. Hopefully, from the beginning, the maintenance department had a role in selecting the equipment. If you didn't, there's a pointer. You should take a look, because this is a gap. Maintenance should be helping to determine what equipment is coming into the plant. Second, manufacturers' recommendations are a start. Usually the manufacturers have recommendations for how maintenance should be carried out on their machinery. You don't need to read it like it's the Bible, but you can take it as a starting point and refine it to meet the needs of your production process. Let's establish some performance improvement targets. We talked about process availability improvement a few times already, but let's look at it. You should really trend process availability over a period of time and make sure that it's increasing and going in the right direction. At the very least, it should be leveled out where you're satisfied with the performance and availability of your equipment. And in that situation, you'd be doing that because you were already at the point where your maintenance costs were minimized and your productivity was acceptable. You can take a look at some technology called reliability analysis and reliability growth. For the most part, this is a computational method used to quantify reliability improvement over time based on a variety of causes. It's used in a lot of cases by manufacturers to try to figure out ways to make their products more reliable. So you might actually be using it in your production process to make your own product that you sell more reliable as you push it out the door. It's kind of interesting. It's like reliability inside reliability. But every piece of equipment and every process does have different factors that affect its reliability, and this can be analyzed. And over time, as you make it more and more reliability, this is called reliability growth. We can also look at maintenance cost reduction and overall performance. Be aware that gross cost reduction, for example annual spending on maintenance, is not really a relevant measure if production and equipment condition suffers. I've seen so many facilities, when they get into a money crunch, decide to stop doing maintenance on their production equipment for a period of time. And it helps because they reduce their costs for the short term, and their equipment tends to run through for a period of time with no problems. But the ultimate issue is, pretty soon the equipment reliability starts to fail and the costs go up. You don't really save anything. It ends up costing you big time. Maintenance cost reduction per unit of quality production is an often more useful calculation. If you're measuring your costs and you're dropping your maintenance costs for every piece of equipment or product that you put out, then you're doing a good job. Let's take a look at another measure, percent reduction in unplanned maintenance. It's really the same thing as percent planned maintenance in reverse. But unplanned maintenance as a percentage should drop to less than 20% in a good proactive organization. I've seen it well below 5% in operations that aren't doing anything magical to get there. They just plan and schedule, and they do things to increase reliability every day continuously as a part of their culture. Let's touch again on overall equipment effectiveness. We did a detailed example of this in Lesson 2. So take a look back at that if you still have questions. But I really don't have anything more to say about it than that. OEE is important to measure, and it's useful in a lot of facilities. Process capability improvement. We want to improve the process's capability based on business goals. In other words, you don't want to go and spend a ton of money on improving process capability if the process is already capable enough to reach the business goals without spending anything. You want to balance production and reliability efforts with the goals of the company. You don't need to be doing unnecessary things to make reliability or productivity go up beyond the need of the business to meet the goals. This is a hard thing for people to understand sometimes, because if your job is to make things more reliable, you want to drive it to be as reliable as possible. Well, in some cases, it's just not worth it. You have to take that into account. Here's another garden variety measure that I use all the time. Percent planned and scheduled maintenance. Shoot for 80% minimum. What we're talking about here is actually work that's been well planned and scheduled. You should be doing that at all times, trying to get 80% of your work through a planning and scheduling process and getting it executed as scheduled. And when I say that, I mean on the day it was scheduled, not the week. So many facilities try to just massage the numbers by moving jobs around during the week. If you're doing good scheduling, you're scheduling it on the day, time, and with the right personnel every day. So what does planned and scheduled work include? Well, it includes all of your preventive maintenance tasks because they're planned by definition. If they're not, what are you giving to the maintenance people to do preventive maintenance? There must be something. Second, predictive maintenance. Predictive maintenance can all be planned and scheduled. Third, planned work completed as scheduled, and we just talked about that. It's got to be completed on the day it's scheduled to count. It does not include breakdowns or expected volumes of emergency work. I've seen quite a few of my clients try to discuss the fact that they plan to have emergencies, so the emergencies are planned work. That's just not the case. Emergencies are emergencies. They're breakdowns and other things that interrupt planned work. They're not counted. Here's another measure, return on net assets, or RONA for short. Return on net assets is a calculation that's done as follows. RONA equals the net income of the facility divided by the sum of the fixed assets and the net working capital times 100%. so it gives you a percentage figure. The higher the figure, the better. So let's take a look at a really simple example that's based on reality. This is from a client of mine from not too far back. The company was operating under kind of stable conditions, and then it was purchased by another company, and some sweeping changes were made to the way production was done, and they went to a fully proactive operation. Let's take a look at how that affected them. Keep in mind, they didn't do anything different with the equipment, they just changed the way they worked. Under the old owner, the net income at the facility per year was $4.8 million. The fixed asset value of the facility was $900 million, just short of $1 billion worth of equipment, and they had no net working capital. Hence, they were selling the facility because they were out of cash and the profits were just not that great. They were spending quite a bit more money to keep the place running than they had. So when you do the calculation as based on the RONA formula shown above, they had a 1% return on net assets. 1%. Now if you think about it, if you were to take $10 and put it in the bank in a plain old savings account at a bank, you could have done better than this. Now let's take a look at what the new owners did. Well, they made some changes to reduce waste. As we talked about in the past, reducing waste is everything. Reliability is 4 to 9 times cheaper than reactive maintenance. That was one aspect of what they did. They also saved a bunch of money on the production side by eliminating some unprofitable grades and products and focusing on things that made money. Their net income for the first year they were in operation went up to $120 million per year with the same exact equipment that was used by the old owner. The fixed assets stayed the same. They didn't spend any money on capital equipment. They just ran the machines and ran the process to make money. Their net working capital was $270 million. Because this company was in a little better shape, they had some capital to work with, but they really didn't need the money to do what they were doing. They were paying for everything from their profits. But doing the calculation for RONA, we came up with a 10% figure. Look at that, a 10 to 1 increase by doing nothing except becoming more reliable and running your process like a business. Now look at 10% is a pretty good return. This happens to be a fairly capital intensive industry that we're talking about here, and I'm not going to tell you what it is, but 10% return is not too bad. In fact, the way the stock market's been behaving the last few years, a 10% return is something that you should be pretty happy with. This company, I'm sure, is going to increase that return on net assets beyond 10% as we move along. I'll be interested to see how high they can drive it. Now we need to talk about selecting some tactics to meet the targets and close the gaps. Here we go again. Targets and gaps. Targets and gaps. This is everything. Really, you need to get into the mindset that to make change, you need to measure, you need to find the gaps, and then you need to close the gaps, and you need to keep refining from there on. I don't know how many times we're going to cover this in the next few lessons, but I would think that you'll have it pretty much memorized by the time we're done with lesson 9. First, let's select and apply appropriate maintenance practices for equipment where the requirements are clear. For equipment where the requirements are clear. First, restoration and replacement activities. Okay, those are things that we need to do and they're appropriate. Condition-based maintenance activities. We can do those too on equipment where the requirements are clear. And failure finding tasks. This only makes sense. Let's continue on with this discussion under some different types of equipment. Now let's select some tactics to meet targets and close the gaps. Here we go again with the targets and gaps thing. It's a repeated thing that we talk about throughout lessons 1 through 9. You'll be sick and tired of it by the time we're done, but it's really what drives all the change. First off, we're going to perform an analysis to identify appropriate maintenance practices where the costs are high, reliability is low, or chronic problems exist. These are the things we talked about in the Pareto analysis. The heavy hitters, the top 10 things that are causing your problems. You want to convert these pieces of equipment into the ones that behave as expected on the previous slide. How would we do that? Well, we talked about it already. Root cause failure analysis, the use of failure modes and effects analysis, or FMEA, and reliability-centered maintenance analysis. These three tools, which are similar in many ways and can be used together, will allow you to make the equipment more reliable, more consistent in operation, and much less expensive to maintain. Well, we've reached the end of Lesson 4, Equipment and Reliability 1. We've talked about a lot of things, we've looked at a lot of information, and I hope it's been useful to you. So let's summarize what we've covered. First, we established equipment and process performance expectations so the measures have meaning. Second, we've measured the current performance and identified the gaps or the baseline, again for the 15th time. These are things that we're going to continue to do as we go along. Analyzing these gaps is how we develop our action items. Third, we're going to design a maintenance strategy that assures operational performance. In other words, if you know how to measure it, you know what the problems are, and you have a plan for getting rid of them, then if you work together with maintenance and production, you're going to eliminate those failures if you keep at it and you stay focused on the ball. So let's take a look ahead into Lesson 5. In Lesson 5, Equipment and Reliability 2, we're going to continue talking about designing a maintenance strategy that assures performance, which we've already been talking about in the last part of Lesson 4. Second, we're going to justify the tactics for implementation, so everybody understands why they're happening and the leaders at the top can support us and give us all the help we need. Third, we're going to apply your workflow process and maintenance strategy for maximum results. And last, we're going to measure performance and adjust for maximum return. Again, looking at the gaps, adjusting, maximum return. We're talking about dollars here. It always comes down to dollars. Congratulations, you've completed Lesson 4. Lesson 4 was a big area, covered a lot of territory. Lesson 5 is going to be a busy one too. Hang in there. Equipment reliability is a really key element. It's a big chunk of the SMRP standard, and it's really got a lot of the root things that you need to be good at to do a good job with maintenance and reliability. So thanks for hanging in there. We'll see you in Lesson 5. Have a good day.